Good morning. In few classes, last classes, we have learnt on multi-step methods, both explicit and implicit. So, now it is very important to learn about the convergence and stability aspects of multi-step methods. We have learnt similar aspects for single step methods. However, the concepts for the multi-step methods are more involved. Okay. So, let us have a quick recall on the multi-step methods before we discuss on the convergence and stability aspects. Okay. So, convergence and stability of multi-step methods. So, recall we have general linear k-step method, so this is just B n. So, this is a general, and in this if B 0 is non-zero, implicit, B 0 is 0, explicit. Example, so this is explicit. So, this is implicit and explicit. So, this is explicit method, because to compute y n plus 1 we are asking past points y n and y n minus 1, whereas here to compute y n plus 1 we are asking y n n minus 1 and plus 1. Okay. So, this is implicit and this is explicit. Okay. So, now what is the definition of convergence? Okay. So, the linear multi-step method of the form. So, of the form. So, let us say this is star, okay, of the form. We can even write it, because star means of the form y n plus 1 is okay, of the form, okay, is said to be convergent if for all IVPs subject to the hypothesis of Picard's existence theorem. So, that means if you recall, when we defined IVP, we assumed that the solution exists subject to the Picard's existence theorem. So, whatever the hypothesis, okay, under those, for example, Lipschitz condition, etc. Okay. So, we have h goes to 0, y n equals to y of x n, where x minus x 0 is n h for all x belongs to a b, and for all solutions of the difference. See, for this this is we have approximated the given IVP with the difference equation. So, now we are talking about convergence of this particular solution of the difference equation. Okay. So, as h goes to 0, this approximated is equal to the exact for all x within this interval, and for all solutions of the difference equation with the starting conditions that are consistent. Okay. So, what is this? That is some y s equals to say eta s of h, okay, where s equals to 0, 1, k minus 1, okay. For which limit h goes to 0, eta s of h, this equals to y 0, s equals to, okay. So, that means these are all y s are, as h goes to 0, they go to initial condition. Okay. So, this is general convergence, and one must understand that it is within the framework of h goes to 0. Okay. So, this is convergence. So, there are some necessary conditions, okay, for a linear multistep method to be convergent. Necessary conditions for convergence. 1, necessary condition for the convergence of the linear multistep method, okay, is that the method be zero stable, I am underlining, to necessary condition for the convergence of the linear multistep method is that the method be consistent, I am underlining. So, we have learnt a method. Okay. So, now the approximation, how this approximation gives converging solution. So, the convergence we have defined. Okay. So, now there are certain necessary and sufficient conditions. Okay. So, what are they? In some sense these conditions are telling, one is zero stability and the other is consistent. So, in some sense one can state necessary and sufficient condition for convergence, or stability and consistency are the necessary and sufficient conditions for convergence, but we do not know, we did not discuss what is zero stable and what is consistent. Okay. So, let us try to understand what is zero stable and what is consistence of a linear multistep method. Okay. So, what we are discussing, zero stability. Okay. Zero stability. So, some of the definitions I am taking from a book, Zuli. This is a numerical solutions of ordinary differential equations. Okay. So, let us define what is a zero stability. Y 0 initial condition given and our IVP is f of x y. Okay. Y 1, y 2, y k minus 1 need to be computed using any known method, of course explicit, because for a multi-step method this is IVP, but we need past points, right, data at past points. So, this we have to compute using any known method, explicit, say Rangakotta. So, what is the general strategy? One can compute using Euler method, Taylor series, Rangakotta. See, what is our ultimate aim? Our ultimate aim is to get as better solution as possible, okay, as accurate as possible. So, for this to happen, the general predictions, you see Euler method is just it's a first order kind of method, right. So, it is first order method, then Taylor series, well, if you use up to second order it is fine, beyond that the calculations are little tedious and all that. So, if the sensible method which is in hand is RK method, and that too fourth order. So, in general, given a linear multistep method, if one has to compute the past points, generally one is tempted to use fourth order RK method. Okay. Yeah. So, let us look at 0 stability. So, these are initial conditions given and these need to be computed using any known method. Okay. Hence, what happens? Hence, all y n's n greater than or equals to k contain error, because these are computed using some known method. So, there is an error. So, that gets in to compute the higher values. Okay. So, let us define what is a 0 stability in this context. Okay. So, the definition okay. A linear multi-step method, okay, for the IVP y dashed equals to f of x y, y of x naught is y naught is said to be zero stable if there exists a constant k such that for any two sequences y n and y n hat which have been generated by the same formula, that means by the same method, but different initial data okay, mod. Okay, what we are going to conclude. So, we have given a IVP, we have given a linear multi-step method, then we say this method is 0 stable if there exists a constant k such that for any two sequences, okay, two different sequences which are being generated. See, we are talking about the same method. Okay. For a given IVP, we are talking about the same method and we would like to conclude when do you say this method is 0 stable. So, the strategy is very intuitive. Okay. So, what it says? It says when do you say this is sensible, this method is 0 stable, means it is giving solutions which are sensible. Okay. That means stability in the sense if there are errors in the past data, then they are not really magnified to a large extent, they are bounded within some extent. Okay. So, when do you say it is this method is 0 stable? We are trying to compare two different sequences, and what kind of sequences? You start with some set of initial data and then you compute the past values, start with another set of initial data and then start with, but the difference equation is same. Okay. So, we are talking about that these two they should be comparable in terms of the initial data. Okay. So, how they are comparable, let us see. So, this difference is less than or equals to k times max of okay, for x n less than equals to say some x m as h goes to 0. So, this is very important. So, what did we do? You start with two sequences, for any two sequences which have been generated by same formula, but different initial data. This is one set of initial data, this is another set of initial data. Of course, the solutions will be different. You start with one set of initial data, you arrive at some solution, and you start with another set of initial data, you arrive with the corresponding solution. Okay. Because after all, the solutions are the curves, right. So, we have this difference should be bounded by constant times maximum of the difference between the solution at a particular grid point. Okay. So, at each grid point you take the maximum, and that will be k times of that. So, that will be the at the nth stage. Okay. So, this is the 0 stability. Okay. So, that means it is not growing beyond the maximum value at a particular grid point. So, now the question why 0 stability. Okay. So, it is in some sense one can decide whether a method is zero stable or not by considering only y dash equals to 0. So, that is f of x y equals to 0. So, this is possible, but very tedious, the corresponding analysis. So, that is how the word 0 has come. That means, whatever the definition we have given for 0 stability, that can be verified by considering just y dash equal to 0, but the analysis is a little involved. Hence, 0 f is 0, therefore, the 0 stability. So, then if that is difficult, what is the alternative? So, the alternative is some algebraic method, which is equivalent to the analysis of f equals to 0 case. Okay. So, some algebraic in the sense, okay, you verify a certain condition and then conclude that the method is 0 stable or the method is not 0 stable and things like that. So, what kind of corresponding algebraic condition? So, that is called root condition. Okay. So, that means instead of doing this tedious analysis, we pick up this alternative and try to analyze and conclude that a method is zero stable or not. But before that, so what is this root condition? We must know. Unless we know what is root condition, we cannot proceed. Okay. So, let us try to see what is root condition. Okay. Right. So, root condition so linear multistep method. So, of the form star, I am forced to write here star because I mean same method we had write. So, let us call star is set to satisfy the root condition if the roots of the equation rho of z equal to 0 lie inside the closed unit disk in the complex plane and the roots are simple if they lie on the circle. Okay. Of course, I wrote something which does not make any sense. Yeah, this quantity we haven't yet defined, but it is some condition. What is it? Linear multistep method of the form star is said to satisfy the root condition if the roots of the equations rho of zeta equals to 0. So, that means this is a polynomial lie inside the closed unit disk in the complex plane and are simple if they lie on the unit circle. So, now what is so this is first characteristic polynomial of a linear multi-step method. Okay. So, linear multi-step method, first characteristic polynomial. What is it? Okay. So, we have not discussed. So, we have to define. So, it is interlinked. So, we have defined is 0 stability and then method is 0 stable if it is satisfies the root condition, etcetera. We will say. Okay. So, let us see characteristic polynomials corresponding to a given linear multi-step method. Okay. So, what is our method? h times okay. So, this is our method, right. So, now this can be put it in the form minus sigma a I okay, all the terms, then minus h equals 0. Okay. So, this is a linear multi-step method. Now, so let us identify these terms. Okay. Let us identify these terms. We have E y forward operator is defined as follows. Okay. So, now we make use of, let us look at y n. Y n plus 1 is E on y n and y n minus 1 is E square on y I am sorry, y n plus 1 is E square on y n minus 1 E on y n. So, that means E on say y n minus 1 is y n, E on y n is y n plus 1. Okay. So, therefore, E 2 on y n minus 1 is E 1 E is y n and this is n plus 1. Okay. So, like this, these can be converted and we have coefficients. Okay. So, let us see how this can be simplified with respect to notation point of view. So, we have y n plus 1 minus okay. So, now in terms of the forward operator, okay, define. So, what will be the last term? Last term of this is this summation is okay. So, this is the last term of the summation. Okay. Now, E y n minus k plus 1, this will be plus 2. Okay. Right. So, this will be k plus 2 3. Okay. So on so forth, right. Okay. So, now 1 E is giving 1. Okay. So, this is like this. Okay. So, this is okay. So, E k. So, if you do the intermediate steps, okay, right. Did you get this? So, you can work out, see this is 1 forward. So, plus 2. So, I am retaining this and it is a plus 1, okay, plus 2. So, E k will be plus k. So, that get cancelled, we get. So, that means this relation, this E k on y n minus k plus 1 is y n plus 1. Okay. So, this is the last, then last but one. What is the last but one? Last but one term contains y n minus k, okay, y n minus k minus 1. So, what will be last term? Y n minus k minus 1. So, it will be this. Okay. So, now how do we express this in terms of y n plus 1? Okay. So, compute E k minus 1, okay, and check it. So, then you will get a hint. Okay. So, accordingly, we have so accordingly I write this as rho of E sigma of E zero, where rho of E is E k, k minus 1, k minus a 2, E k minus 2, okay. Let us try to see. So, if you multiply on this, this is 1. So, minus a k y n plus 1, which is the last term of the summation. Okay. For example, first term E k on n minus k plus 1, E k on n minus k plus 1, n plus 1, this is y n plus 1, and k minus 1 with a coefficient a 1. So, that should be y n minus n y n term. Okay. So, so on so forth. Similarly, sigma E b 0 so these are with plus because I have written minus here. Okay. So, this linear multi-step method can be expressed in terms of this. Okay. So, now we define first characteristic polynomial of a multi-step method. So, this is a polynomial a1 minus a2 minus ak, and the second characteristic polynomial is sigma of this. So, this is b0 okay. So, for a given linear multi-step method, so these are important as within the context of stability of a method. So, we will see how these will play a vital role. Okay. So, having learnt these first characteristic and second characteristic polynomials, for a given particular method, let us see how do we compute these polynomials, okay, just to be more comfortable. Okay. So, for example, so suppose this is our given multi-step method. So, this can be written as okay. So, now look, so this will be E on yn plus 1, but we do not have the terms at these grid points. Okay. We have the derivatives at these grid points, that is n minus 1, n minus 2, but here we do not have. Okay. So, that means the corresponding coefficients are 0, right. So, if you recall, the number of terms here, if you include this as well in the summation, then I starts from 0. Okay. So, where a 0 is 1. So, that means essentially we have k plus 1 terms here, k plus 1 terms here. Okay. That means k plus 1 terms at the grid point and the derivatives k plus 1 terms at the grid points. Okay. So, we must always compare with this. So, in that context, before we arrive at this, we may try to see, okay, we have to arrive at y n from here. Okay. So, how do we arrive? E on y n minus 2 prime is y n minus 1 prime, then E on y n minus 1 prime is y n prime. This implies E 2 on y n minus 2 prime is y n prime. That means, what is the distance from this term to this term? This is E 2. Okay. So, therefore, this suggests your sigma E of the form, okay, of the form. So, if you compare the general method, h is given, minus sign is given. So, I put the polynomial on this. So, all the coefficient must be given to this polynomial. Okay. So, how do we give it? 23 by 12, the distance is 2 minus 16 by 12, the distance is 1 plus 5 by 12, 5 by 12, yeah. Okay. Because this will act on, this will multiply y n minus k plus 1 prime. So, what is the k here? So, this should act on the term of the form y n minus 2. So, we have to suitably identify what is our k. Okay. Right. Okay. So, now what will be this? Okay. Look, this is up to y n, the distance is 2 and here n plus 1. So, naturally the distance must be 3. Okay. So, these two terms accordingly, this gets transformed as okay, exactly. So, we can work it out, right. So, n minus 2 prime and n minus 2. So, therefore, this is and sigma of this is so, for a given multi-step method, this is the first characteristic polynomial and this is the second characteristic polynomial. Okay. And we expect this to be of the form y n minus k plus 1. So, this is y n minus 2. So, therefore, so that means this is a linear 3-step method. Okay. 1, 2, 3. It is asking pass data at 3 grid points 1, 2, 3. Okay. Right. So, now let us go back to our root condition. Okay. So, what it says, the root condition, the linear multi-step method of the form star is set to satisfy the root condition if the roots of the equation, that is the first characteristic polynomial of the corresponding multi-step method, lie inside the closed unit disk. Okay. So, these roots must lie inside the closed unit disk. Okay. So, that means the magnitude must be within the closed unit disk, and if the roots lie on the circle, then we say the roots are simple. Okay. So, these root condition has implications on the stability aspects of the linear multi-step method. Okay. So, let us see some issues related to this. Okay. So, we have seen some example, again we will see y n plus 1 equals to y n plus h by 4, say some 5 y n minus 1 minus 7 y n minus 1 prime plus y n minus 2 prime. Okay. So, if this is the case, then what is our row of zeta? So, this is only these two, right, and this is a 3-step method. So, this will be zeta square minus 1. Okay. This implies so, this is our characteristic polynomial, zeta equals to 0, zeta equals to plus or minus 1. Okay. Right. So, the linear multistep method of the form is said to satisfy the root condition if the roots of the equation lie inside the closed unit disk. Okay. And the roots which are on the circle, they are called simple. So, these is within the unit disk, and these two are simple roots of the corresponding linear multistep method. Okay. So, we have to see some outline of necessity, means what to do with the root condition. Okay. So, consider our method in a more general form. We convert to a multistep method, and then the corresponding first characteristic polynomial is of this form, and general solution is, so this is a difference equation, because our whose general solution is of this form, some f s of n z s of n, where z s are roots of this. Okay. So, now if the magnitude is greater than 1, this suggests that if the magnitude of this is greater than 1, okay, so this suggests that what will happen to this, and other cases. So, this z s equals to 1 and multiplicity m s greater than 1. So, these are the two troublesome cases. What are they? Magnitude is larger than 1. So, then we have to worry about this, and the other case is multiplicity is greater than 1 of a unit root. Then you see this has a specific format, okay, from our solutions of difference equations or any recurrence relation. You can see if a root has a multiplicity. So, then we have, so the general is a linear combination is say C 1 z 1 power n, C 2 z 2 power n. So, this is general. Okay. If you have multiple roots, then some d 1 plus n d 2 and say some z 2 has multiplicity m. So, then we have this kind of okay. So, in these cases there is a chance that leads to unboundedness. Okay. So, leads to unboundedness. So, this is just an outline of necessity, why root condition is really necessary. So, what is to do with root condition? This is the first characteristic polynomial and you compute the roots, then depending on the behavior of the roots, the solution behaves. So, how it is possible? See, we from here the general solution is of this form. So, if the roots are magnitude is larger than 1, there is a chance that it gets unbounded. If the roots are within this that means on the boundary of the unit circle, but multiplicity 1, then this may happen, and then again that may lead to unbounded solutions, right. So, therefore, root condition play a vital role. That is how root condition has become into play. Okay. So, for example, consider Euler method y n plus 1 equals y n plus h f n. So, what will be the characteristic polynomial? So, rho of z is okay, right, and implies this is the characteristic polynomial z equals to 1 okay, is a simple root. Okay. Z equals to 1 is simple root. Then consider another method. So, for this method, so z or zeta, I was using zeta earlier. So, this is 11 zeta cube minus 27 zeta minus 11. This is our characteristic polynomial, and the roots are approximately okay. So, mod zeta 3 is greater than 1, therefore, the method is not 0 stable, because it fails to satisfy the root condition for this case, right. So, root condition play a vital role. How? The outline I have given. So, if one of the root magnitude is 1, then the solution is unbounded. Okay. So, therefore, root condition play a vital role. It becomes a necessary and sufficient condition for a method to be 0 stable. So, we learn further more details about this in the next lectures. Okay. So, you may practice for a couple of formulas how to compute the first characteristic, second characteristic polynomial. Okay. Thank you. Bye.